Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is class 3, and today we go deeper inside the atom. Last time, we watched Bohr draw neat little orbits, like planets around the sun. But nature is subtler than that. An electron has no fixed path at all, only a home address, written in 4 numbers, and a hazy cloud of space where it is most likely to be found. When Sarah first heard this, she asked, if we cannot say exactly where the electron is, how can JEE ever build a numerical out of it? And that is exactly what today is about. We will turn that address book into a node count numerical. A race between 2 orbitals for who fills first, and the famous chromium-copper anomaly. Today, one idea at a time, we learn to read that address, draw that shape, and fill every atom with confidence. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the 4 quantum numbers N, L, M, and C, the full address that names exactly where an electron lives. Second, the shapes of the s, p, and d orbitals, and the node count numerical that JEE loves to hide inside them. Third, the 3 great filling rules, Aufbau, Pauli, and Hund, and the n plus L rule that decides which orbital fills first. Fourth, electronic configuration, and the famous chromium and copper anomaly, where the atom breaks the simple pattern for the sake of stability. And fifth, the JEE drills, assertion and reason, match the column, and a full numerical quick check, so that everything you learn today you can also score with. Ready? One idea at a time. Every electron in every atom has a unique address, and that address has 4 parts. The first is N, the principal quantum number. It names the shell, and it sets the size and the main energy level. N can be 1, 2, 3, and so on. Bigger N means a bigger, higher energy orbital, farther from the nucleus. Think of it as the floor of the building. The second is L, the azimuthal quantum number. It names the subshell, and it decides the shape. L runs from 0 up to n-1, and we give its values letters. L equal to 0 is S, 1 is P, 2 is D, 3 is F. So L is the shape of the room. The third is M, the magnetic quantum number. It names the orientation, which way the orbital points in space. For a given Lm, takes 2 L plus 1 values, running from -L through 0 to plus L. So a p subshell with L equal to 1 has 3 orientations, 3 p orbitals. And the fourth is S, the spin quantum number. Each electron spins one of 2 ways, +1/2 or -1/2, spin up or spin down. 4 numbers, 1 electron, 1 unique address. No 2 electrons in an atom can ever share all 4. And this exact rule becomes Pauli's principle in a few slides. Now let us actually see these homes, and this time look extra carefully, because JEE turns this picture straight into a numerical. The s orbital is a simple sphere, one smooth ball of probability around the nucleus, the same in every direction. When L is 0, there is no preferred direction at all. The p orbital is a dumbbell, 2 lobes stretched along an axis, with the nucleus sitting in the pinch between them. Because L is 1, there are 3 of these dumbbells, pointing along the x, the y, and the z directions. The d orbital is more elaborate still. 4 lobes, a cloverleaf shape, with L equal to 2 and 5 different orientations in space. As L grows, the shapes grow richer. And here is the formula that ties them together. The total number of nodes in any orbital is n-1. The angular nodes equal L. The radial nodes equal n minus L minus 1. Picture the 2s orbital on screen. The thin dashed ring cutting through it is exactly 1 radial node, a spherical shell where the electron is never found. Hold this formula close. JEE builds whole numericals out of it. Let us slow right down on nodes, because this is where easy marks are won and lost. First, what is a node? A node is a region of space where the probability of finding the electron drops to exactly 0. The electron is on either side of it, but never in it. Second, the angular nodes. These are flat planes that pass through the nucleus, and their number equals L. So an s orbital with L equal to 0 has no angular nodes, while a p orbital with L equal to 1 has 1. Third, the radial nodes. These are spherical shells of 0 probability nested inside the orbital, and their number equals n minus L minus 1. And now the beautiful part. Add the angular and the radial together. L plus n minus L minus 1, and the L cancels clean away. What remains is simply n minus 1. So the total number of nodes in any orbital is always n minus 1, no matter its shape. Now the G twist. A full numerical that traces two orbitals against each other, solved slowly, the monk's way. Compare the 3D orbital against the 4p orbital. Which one carries more energy, which one fills first, and how many nodes does each one hide? Step 1. Write down what is given. For 3D, n is 3, and L is 2. For 4p, n is 4 and L is 1. We must compare their energy and count the nodes in each. Step 2. Add n and L for both. 3D gives 3 plus 2, that is 5. 4p gives 4 plus 1, that is also 5. The two sums are exactly equal, a tie. Step 3. Break the tie. Whenever two orbitals share the same n plus L value, the one with the lower n fills first. 3 has a lower n than 4, so 3D fills before 4p, even though 4p is written with a bigger number. Step 4. Count the nodes in 3D. Total nodes equal n minus 1, that is 3 minus 1, 2 nodes. Angular nodes equal L, that is 2. Radial nodes equal n minus L minus 1, that is 3 minus 2 minus 1, 0. Step 5. Count the nodes in 4p. Total nodes equal n minus 1, that is 4 minus 1, 3 nodes. Angular nodes equal L, that is 1. Radial nodes equal n minus L minus 1, that is 4 minus 1, 2 dia. Same tie-breaking logic, same node formula, one numerical, G's two favorite ideas at once. Now the master map, the order in which orbitals actually fill, and the very same 3D, 4p tie from a moment ago, seen on the staircase itself. First, the Aufbau principle. The word means building up. Electrons always occupy the lowest energy orbital available before moving to a higher one, filling the atom from the ground floor upward. Second, how do we know which orbital is lower? By the n plus L rule you just used. For each orbital, add n and L together, and the orbital with the smallest sum fills first. Third, when two orbitals tie on n plus L, exactly like 3D and 4p, both summing to 5, the one with the lower n fills first. Look at the two dashed circles on the staircase, that is the tie we just solved. Fourth, the practical trick. Just follow the diagonal arrows down the staircase, one after another, and you will never light the order wrong. Lisa used to memorize the sequence by force and kept slipping. The day she started drawing the arrows, the order became automatic. Now sit up straight. These 5 lines are what JEE actually asks, year after year. 1. The total number of nodes in an orbital is n minus 1. The angular nodes equal L, and the radial nodes equal n minus L minus 1. This trio is tested constantly, and now you can also build a full numerical from it. 2. Each subshell holds 2 L plus 1 orbitals, the same count that decides how many magnetic quantum values and how many degenerate orbitals a subshell has. 3. The Pauli exclusion principle says no two electrons can share all 4 quantum numbers, so an orbital holds at most 2 electrons with opposite spins. Hund's rule says electrons occupy separate orbitals singly, with parallel spins before any pairing begins. And half-filled or fully filled subshells are extra stable. 4. The n plus L rule sets the filling order, and whenever 2 orbitals tie on that sum, the over n wins. This is exactly why 3D fills before 4p, even though both sum to 5. 5. Remember the 2 anomalies called? Chromium is 3d5, force 1, and copper is 3d10, force 1. Exchange energy is what stabilizes a half-filled or fully filled D subshell. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one. Assertion, chromium's configuration is 3 to 5, force 1, not 3 to 4, force 2. Reason, a half-filled 3D subshell gains extra exchange energy stability. Think like SATA. Check each statement on its own, then check the connection. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. Chromium moves an electron precisely to reach that stable half-filled D. Both true. Reason explains. Option A. Second one. Assertion, the force orbital fills before the 3D orbital. Reason, the 3D orbital is spherical in shape. The assertion is true by the n plus L rule. But the reason is false. The 3D orbital is a cloverleaf, not a sphere. Only s orbitals are spherical. Assertion true, reason false, option C. This is the trap that catches John, who accepts a true-sounding reason without checking it. Third one, assertion, between 3D and 4p. Either orbital may fill first, since their n plus L values are equal. Reason, when n plus L values tie, the orbital with the lower n fills first. Check the reason. It is true. Exactly the rule we just used. Now the assertion, if the tie is always broken by the lower n, then it is not true that either may fill first. 3D always fills first, never 4p. The assertion is false. The reason is true. Option D. A quick match now. Say each node count aloud before I reveal it, using total nodes equal n minus 1. The 1, s orbital, n is 1, so n minus 1 is 0. 0 nodes, the smoothest orbital that is. The 2p orbital, n is 2, so n minus 1 is 1. 1 node. The 3d orbital, n is 3, so n minus 1 is 2. 2 nodes. The very orbital from our worked example. And the 4f orbital, n is 4, so n minus 1 is 3. 3 nodes. Notice the formula works the same way whether the orbital is an s, a p, or an f. If all 4 came to you before the reveal, the formula is becoming yours. Here's a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. For the D subshell, where L equals 2, the 5m values give 5 orbitals. Ojo verdict. Statement 2. Copper's ground state configuration ends in 3d9, force 2. Recall the anomaly we just met. Statement 3. 2 electrons occupying the same orbital must have opposite spins. This is in fact the very rule Pauli is named for. So, how many are correct? 2 statements. The first and the third. The D subshell truly gives 5 orbitals, and 2 electrons sharing an orbital truly must be opposite in spin. But the second one falls. Copper's true configuration ends in 3d10, force 1, not 3d9, force 2. Copper reaches for a fully filled D, not a nearly full one. Now let me save you some marks. 2 traps that catch thousands of students every year. Myth 1. The number of nodes in an orbital equals n. It feels tidy, but it is wrong. David believed this for months and kept overcounting. The truth. The total number of nodes is n minus 1, never n. A force orbital has 3 nodes, not 4. Always subtract 1. Myth 2. 4p fills before 3d. Simply because 4 is a bigger number than 3. The truth. Both orbitals sum to the same n plus L value of 5, and whenever 2 orbitals tie on that sum, the one with the lower n wins. 3d with the lower n fills first, before 4p, never after. Time to test yourself, rapid fire, and today it is all numbers. Here is the rule. I ask, you answer in your head before the reveal and spell the number to yourself. No pen, no paper, just the formulas you built today. Question 1. How many total nodes are in a 4p orbital? Total nodes equal n minus 1, so 4 minus 1, 3 nodes. Question 2. How many radial nodes are in a 3d orbital? Radial equals n minus L minus 1. So 3 minus 2 minus 1. 0 radial nodes. Question 3. How many angular nodes are in a 4f orbital? Angular nodes equal L, and for F, L is 3 angular nodes. Question 4. How many orbitals are there in an F subshell? Using 2L plus 1. L is 3. So 2 times 3 plus 1, 7 orbitals. And question 5. The classic. 3D and 4p tie. At an n plus L value of 5, which one fills first? By the tie-break rule, the lower n wins. So 3D fills first. If you caught everyone, you've truly understood today's class. Let us gather the whole class in one slow breath. 4 quantum numbers, n, L, m, and s, together give an electron its full and unique address inside the atom. The s orbital is a sphere, the p a dumbbell, the d a cloverleaf, and the total number of nodes is always n-1. Each subshell holds 2L plus 1 orbitals, and Pauli and Hund together decide how those orbitals fill. The n plus L rule sets the order of energies, and whenever 2 orbitals tie on that sum, the lower n wins. 3d before 4p. Chromium is 3d5, force 1, and copper is 3d10, force 1. Half-filled and fully filled subshells are exchange energy stable. And next class, we step back to see the whole family, periodicity, the periodic table, and how properties repeat in beautiful trends across it. Do not miss it. And so, my friend, we have gone right inside the atom. G level. It may have looked like just 4 numbers, a few strange shapes, and one tie-breaking rule. But understand this. Everything about an element flows from where its electrons live. Its size, its reactivity, its very place in the periodic table, all of it is written in the configuration and the energy order you learned to read today. Sarah, David, Lisa, and John all started exactly where you are right now, with this one class. Be patient with yourself. Tonight, once slowly, work out the 3D, 4p race by hand, and write out chromium and copper alongside it. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you at the periodic table.